Hello, my name is Wesley Williams. Today I'm going to be talking about UIO66, a zirconium-based metal organic framework, or MOF for short. One of the biggest focal points for the scientific community right now is the increase in the concentration of carbon dioxide, or CO2, in our atmosphere. Because of the way the CO2 molecule is arranged, it can vibrate in 3 different ways. All these different modes of vibration allow CO2 to be able to capture and release heat in ways that some other atmospheric gases, like nitrogen and oxygen, do not. This is concerning because the increase in CO2 can be a big factor in global warming. Also, according to one study, there's a significant risk in the decrease of biodiversity. This could mean the extinction of tens or even hundreds of species of animals over the next century. To try to prevent this from happening, many in the community have been researching ways to capture CO2 from the atmosphere. Over the past 20 or so years, MOFs have become more and more popular as a means of gas capture and storage. MOFs are comprised of a crystalline structure, as you can see on the poster, that typically features porosity. The porous nature of the MOF allows it to capture and contain gases in a more orderly fashion than if the gas was free to move about its container. This is because, depending on the structure of the MOF, gas molecules can come to rest inside the pores rather than quickly moving about their container as they typically would. MOFs have 2 major components, a metal cluster and organic linkers, which act as the framework's struts. These linkers can be tuned with different functional groups that exhibit a variety of properties. Here, several organic linkers have been utilized in order to form different versions of UIO66. Some MOFs also have the ability to catalyze the reduction of CO2 via their open metal sites. CO2 can come into contact with these sites and undergo a reduction reaction. Guest host molecular arrangements have also been researched as a means of reaction within the MOF's pores. Using nanocomposites can also play a role in carbon dioxide reduction. In this experiment, several varieties of UIO66, a zirconium MOF, were formed with the interest in their ability to capture and store gas. Synthesis was done as is shown in the poster. A combination of BDC and zirconium chloride were dissolved in DMF and methanol. They were then heated in an oven at 120 Celsius for a day to form the MOFs. These MOFs were characterized using SEM, IR spectroscopy, and X-ray diffraction techniques. The structure of the MOF was confirmed by comparison of our XRD with the cataloged version. Further testing can be administered to better understand which type of linker is optimal for the capture of CO2. In future work, different nanocomposites can be attempted to optimize the reduction reaction of CO2. This could have implications for the future of our environment as we continue searching for ways to reduce our carbon footprint and make chemistry more green. Thank you.